Have you ever been on a plane, you're looking out the window at that giant wing, and you just kind of wonder, how? How does this massive metal tube even get off the ground? Well, a huge part of the secret, it's hidden inside the metal itself. And it's a story that starts all the way down at the atomic level.
Okay, so take a look at this. This is what's inside the wing of a Boeing 767. It's this incredible, complex skeleton of beams and supports. And the truly mind-boggling part? The whole thing is made out of aluminum.
And that really is the question, isn't it? I mean, when we think of aluminum, we're thinking of soda cans you can crush in one hand, or kitchen foil you can tear with your fingers. So how on earth is that same soft, lightweight metal strong enough to carry hundreds of tons through the sky and deal with just unimaginable forces? Well, the short answer is, it's not. Not the aluminum you're thinking of, anyway. The stuff holding an airplane together is a completely different beast from what's in your kitchen drawer.
See, it's an alloy. An alloy is really just a metal that's been beefed up by mixing in other elements. It's kind of like a recipe. You're taking the best properties of one metal, like aluminum being super light, and you're adding new properties, like incredible strength.
For airplanes, the key ingredient they add to the aluminum is copper. And copper has this really unique property that's crucial to this whole thing. At high temperatures, it dissolves into aluminum super easily, but at low temperatures, it doesn't. And that one little fact, that is the key to unlocking its hidden strength.
Because, just mixing the two metals together, that's not the magic trick. The real transformation, the real magic, happens with a very specific multi-step heat treatment. The official name for it in materials science is precipitation hardening.
Think of it like a recipe for ultimate strength. First, you've got solution treatment. You heat the alloy way, way up. This lets all those little copper atoms dissolve and spread out evenly inside the aluminum, just like sugar vanishing into a hot cup of coffee. Then, bam, you hit it with the quench, you cool it down incredibly fast. You're essentially flash freezing those copper atoms right where they are, before they can move. And finally, there's aging. You gently warm the whole thing back up just enough to give those trapped copper atoms a little energy so they can start to find each other and cluster together into these tiny microscopic particles.
So, here's the big question. What are these tiny little clusters actually doing? I mean, how does creating a bunch of microscopic particles inside a piece of metal suddenly make it strong enough for an airplane? Well, to get that, we have to think about how a metal bends in the first place.
These tiny particles, they're called precipitates, and their one and only job is to act like microscopic roadblocks. They're designed to just get in the way whenever the metal tries to bend or deform.
Here's a great way to picture it. Imagine you have a giant, heavy rug on the floor. Trying to pull the whole thing at once is almost impossible, right? But the easy way is to make a little wrinkle at one end and just push that wrinkle all the way across. Well, on an atomic level, that's almost exactly how metal bends, through the movement of tiny little defects called dislocations, which act just like that wrinkle in the rug.
And that, right there, is exactly what the precipitates do. They are like the legs of heavy furniture scattered all over that rug. They pin the atomic structure down, making it incredibly difficult for those wrinkles, those dislocations, to move around. And if the dislocations can't move, the metal can't bend. It becomes rigid and incredibly strong.
But creating these roadblocks is an incredibly precise process. They don't just pop into existence. During that aging step, they actually evolve through this whole sequence. They start off as simple little clusters, then they organize into these fine, needle-like structures, then slightly bigger ones, and then finally they become these stable particles. Now, scientists have very specific names for each phase, but the important thing to get is that not all of these phases are created equal when it comes to making the metal strong.
And here is the absolute key to the whole process. It's that middle phase, the theta double prime, the super fine, needle-like particles that gives the most strength. Because they're so small and so perfectly woven into the aluminum around them, they create a massive amount of strain on the atomic structure. They are, as the science says, the most effective barriers you can possibly create. And that's what gives the alloy its peak hardness.
And you can literally see it on this chart. As that aging process gets going, the hardness starts to climb. And then it hits its absolute maximum, its peak, right when the metal is filled with those tiny super effective precipitates. But here's the catch. If you overage it, if you let those particles get too big, the strain actually goes down and the metal starts to get softer again. It is all about stopping the recipe at the exact right moment to get that peak performance.
So, after all the talk about roadblocks and furniture legs, this
This is what it actually looks like. This is an image at the atomic scale. Those darker clusters, those are the copper precipitates, the little fortresses we've been talking about, locked inside the aluminum. You are literally looking at the source of an airplane's strength.
So, now that we've seen what's happening at the atomic level, we can zoom all the way back out and really see how this incredible science translates from tiny atoms to massive airplanes. And the difference is just staggering. On one side, you've got your everyday pure aluminum can. It's soft, it's bendable, it's got really low strength. On the other side, you have an aluminum-copper alloy that's gone through this incredibly precise precipitation hardening recipe. It's still lightweight, but now it has the extreme strength needed to fly. It's the same base element, but it's in a completely different universe of performance.
So if you're going to remember anything from all this, what are the big takeaways? First, just mixing metals together, the alloying, that's only the very beginning. Second, the real strength comes from that super precise recipe of heating and cooling. Third, all that strength is born from creating billions of tiny microscopic roadblocks that literally stop the atoms from shifting around. And finally, and maybe the coolest part, is that some of the most incredible engineering on the planet is happening at a scale so small you can't even see it.
It really makes you wonder, doesn't it? If there's this much complex, elegant science hiding inside a simple piece of aluminum, what other everyday materials around us are holding secrets that are just as amazing?